This is part one of Mars. We start with the key question. Mars. Overview. Mars. Overview. This is where the Mars series begins. The question we're starting with is a simple one. Why does Mars matter so much? And what do we actually know about it right now? That question drives everything in this episode. Because Mars isn't just a destination. It's a record of what a rocky planet can become, and possibly what it once was. Mars sits forth from the Sun at an average distance of about 228 million kilometers. One orbit takes 687 Earth days. A Martian day, called a sol, runs just 40 minutes longer than our own. In some ways, that makes it feel familiar. Don't let that mislead you, though. Mars is a fundamentally alien world, and the differences run deep. Start with the basics. The planet's diameter is roughly 6,779 kilometers, just over half the width of Earth. Its mass is about a tenth of ours, which puts surface gravity at around 38% of what you'd feel standing here. If you weigh 80 kilograms on Earth, you'd weigh around 30 on Mars. Two small moons orbit it, Phobos and Deimos, both thought to be captured asteroids, irregular in shape, and neither likely to last indefinitely. Phobos is slowly spiraling inward. Within the next 30 to 50 million years, it'll either break apart or strike the surface. Here's something that sets Mars apart from almost everything else in the inner solar system. Its surface is split into two dramatically different hemispheres. The southern highlands are ancient, heavily cratered terrain, some of the oldest surfaces we know of anywhere in the solar system. The northern lowlands are younger, smoother, and sit several kilometers lower on average. Scientists call this the Martian dichotomy, and there's still no definitive explanation for it. The leading ideas involve either a massive ancient impact or differences in how the crust cooled in the planet's earliest history. Either way, it's one of the most striking unresolved questions in planetary science. Mars also hosts some of the most extreme geological features in the solar system. Olympus Mons is the largest volcano we've identified anywhere. It stands around 22 kilometers above the surrounding plains, roughly 2.5 times the height of Everest, and spans an area comparable to France. The Valles Marineris canyon system stretches approximately 4,000 kilometers across the equatorial region, reaching depths of up to 7 kilometers. For comparison, the Grand Canyon is roughly 446 kilometers long. Valle Marineris makes it look modest. These structures tell us something important. Mars was geologically active for a very long time. Olympus Mons likely built up through repeated eruptions over billions of years, accumulating layer by layer on a plate that never moved. Unlike Earth, where tectonic drift carries crust away from hotspots, Mars appears to lack active plate tectonics today, though whether it ever had them, and whether any volcanism persists somewhere beneath the surface, remains an open question. Surface temperatures vary enormously. At the equator during summer, daytime readings can reach around 20 degrees Celsius. At night, and especially toward the poles, temperatures can plunge to minus 125 degrees or lower. The atmosphere, mostly carbon dioxide, at less than 1% of Earth's surface pressure, offers almost no insulating effect. Worth keeping in mind for the next episode, that atmosphere wasn't always this thin. There's clear evidence carved into the surface that liquid water once flowed on Mars. Ancient river valleys, lake beds, and minerals that only form in the presence of water all point to a wetter past. Curiosity, exploring Gale Crater, has confirmed the site was once a lake environment, calm enough and chemically stable enough to have supported microbial life as we understand it. Perseverance, working in Jezero Crater, is collecting samples from what was almost certainly an ancient river delta. Those samples are intended for return to Earth by a future mission, and they may be the most scientifically significant cargo ever transported from another world. That leads to the astrobiological question, the one that tends to dominate public interest. Could Mars have once supported life? Possibly. Conditions in its early history, liquid water, a thicker atmosphere, internal heat, may have been broadly comparable to early Earth during the period when life emerged here. We don't know whether life arose on Mars. There are no confirmed biosignatures, but the question is scientifically legitimate, and the search is active. The modern surface, though, is harsh. With no global magnetic field, Mars is bathed in ultraviolet and cosmic radiation. That field was lost early in the planet's history, probably within the first few 100 million years. And without it, the solar wind gradually stripped away much of the atmosphere. That process is ongoing, and NASA's MAVEN spacecraft has been measuring it directly since arriving in September 2014. The implication is significant. What's cold and thin today was once warmer and thicker. Mars had a fundamentally different climate. We've explored Mars more thoroughly than any other planet beyond Earth. More than 50 missions have been attempted since the early 1960s, and around half have failed, which gives you some sense of how difficult it is to get there and operate successfully. Several spacecraft are either orbiting Mars or working on its surface right now. ESA's Mars Express has been in orbit since December 2003. NASA's Mars Reconnaissance Orbiter has been returning detailed imagery and data since 2006. Curiosity has been active on the surface since August 2012. Perseverance landed in February 2021, carrying with it the Ingenuity helicopter, the first powered aircraft ever to fly on another planet. What ties all of this together is that Mars isn't a simple target. Its geological history, written in rock and ice, a cautionary tale about how dramatically a planet's climate can shift. And it may, or may not, carry evidence of past biology. Each of those threads demands its own investigation, and each connects to the others. That's what this series is built around. We'll take Mars apart piece by piece. Its atmosphere and climate, its geology, its water history, and the question of whether it ever held life. The playlist has every episode in order if you want to follow the whole thing. Next time, we look at the Martian atmosphere, how it works now, and what the evidence tells us about how it got this way. If you found this useful, subscribing means you won't miss what comes next. There's a lot more to Mars than most people realize, and we're only just getting started. That is part 1 of Mars. In part 2, we explore the next key question. Subscribe so you do not miss it.